Hi everyone. So we're going to go through the Module 6 review answers. I'm going to have to be quick because I'm only allowed to do a 10-minute video, and I've done this about 3 times already, and I can't fit into 10 minutes. So I'm going to go a bit fast, but at least you'll see that we do have the answers here. Okay, number 1, your answer should have been stoichiometry. Those are the quantities, relating quantities of different substances in a chemical equation. You'd have found that on page 163. The next one is the chemical that is responsible for stopping a reaction is called the limiting reactant, and that was on page 167. Number 3, the limiting reactant that's responsible for determining how much product is produced. Okay, so limiting reactant is responsible for determining how much product, because once you run out of that limiting reactant, that's the most product that you're going to get. Number 4, when determining amounts of reactants and products that are involved in an equation, if all products and reactants are gases. This is a big key thing here, the gases. So as soon as you see gases, you should be automatically thinking of the Gay-Lussac's law, because then you can assume that whenever there's the coefficients, then that means moles, molecules, and then you should have said here liters, as well as centimeters cubed. So cubic centimeters is also a volume. So it could mean any of those things, all right? Number 5 is which formula tells you a simple whole number ratio for the atoms in a molecule. Simple whole number ratio for atoms means empirical formula, and that was on page 186. What is needed in order to convert an empirical formula into a molecular formula? So we're going to go from empirical into a bigger molecular formula, and this was not very obvious, but if you read it closely in the text on page 187, it did tell you that what you needed was the molecule's mass, and we're going to do a problem like that in just a minute. Which of the following molecular formulas are also empirical formula? So molecular formulas are, it tells you exactly how many of each element. An empirical formula is sort of like the recipe, and it is the smallest amount that you can possibly get. So if you can divide any of these little tiny numbers by anything and get something smaller, then it is not an empirical formula. So therefore, this first one, you could divide each of those, the 6 and the 9, by 3, so it is not an empirical formula. B and C are both molecular formulas and empirical formulas, so those are, you should have clicked those as yes. All right, D is not an empirical formula because you could have divided each of these things by 2. So C8H18O2, you could have divided by 2, and so that makes it not an empirical formula. The last one is an empirical formula. Anytime you see 2 and 3 together, you know that those are not going to be able to divide any lower. So that one is an empirical formula as well as a molecular formula. Number 8, this one is from example 6.4 on page 172. And I definitely encourage you to go to your book and find this in the book on page 172. It'll step you through, but each step. But what I want to just show you is how the 2 here for the KAgC2N2 is also the same as the 2 on the other side for the silver. So since it's a 1-to-1 ratio, it's going to be the same number of moles. But it will show you in the book on page 172 how to do each step. Number 9, how many grams of tungsten can be produced if 1.0 times 10 to the 6 grams of hydrogen is used completely? And for that one, we have extra practice problem 2, and that is on page 98 in the teacher manual. What they have you do is they take that 1.0 times 10 to the 6 grams of hydrogen, and then it goes from grams to moles. So remember how we calculate AMU, and since it's hydrogen, it's a H2, so we're not going to take just the 1.01, we're going to take 2.02. So convert from grams to mole, and then once you get to that mole, you're going to look at the ratio of where you see in here the hydrogen, the ratio between the hydrogen and the tungsten is a 3-to-1. And then once you get that you're going to find the number of moles of tungsten, but that's not even the end of the question because it says how many grams of tungsten. So then you're going to have to convert the number of moles to grams just for the tungsten. And this is your answer. You should have gotten 3.1 times 10 to the 7 grams of tungsten. Number 10, I worked that one out down below. Let me just read the question real quick. If a chemist adds 50 grams of HCl and 40 grams of K2CR2O7, we need to find the limiting reactant. You will see this on the test, that you have to determine which one is the limiting reactant. There is a balanced equation here. So let me scroll down and I'm going to show you. This is similar to review question number 3. But first you have to start off with converting the grams to moles. So review question 3 starts off with moles. And this one is starting off with grams. So using the same way we've been doing before, you take the what's given to you, you look at the AMU on the chart and you put what you want on the top, which is mole, and then that's the number of grams based off of how many AMUs there are in HCl. So it's 36.5 grams. Then this gives you the moles of HCl, 1.37 moles. The next step is to convert the 40 grams of K2CR2O7, and that's going to need to be in moles as well. So you'll see you got your answer here, 0.136 moles of K2CR2O7. And then finally, you look at the balanced chemical equation, and you need to figure out how much of the coefficients there are compared between the HCl and the K2CR2O7. And you'll see it's a 14:1 ratio. So we're going to need to take that 14 that's in front of the HCl and, yes, the 14 in front of the HCl, and we're going to multiply that times the number of moles that we got from up here, and that gives us 19.18 moles of HCl. Now, the K2CR2O7 is just a 1 in front of it here, so this is your final answer, the 0.136 moles. So which one is smaller? The smaller one, obviously, that's going to run out fastest is the K2CR2O7 because 0.136 is much smaller than 19.18. All right, so the next one is number 11. I did a separate video on that because it was pretty lengthy, so make sure you check that out on the Google Classroom, but the final answer was C2H2O. You could get extra credit for that. Go to the Google Classroom. Number 12, a substance with the empirical formula CCl2 has a molar mass of 166 grams. This is also called a molecular mass of 166 AMU. So be familiar with the different terms, okay? So what is the molecular formula of the compound? This is just like the second half of practice problem number 10. And when you do that, you'll see that in practice problem number 10, and I'll tell you what page number it is, hopefully if I can find it real quick. Practice problem number 10 is on page, page 43 in the manual, and it shows you how if you add up the mass that you will end up with a certain amount of AMU, and I believe I did it here. Okay, so if you start with CCl2, you would get 1 times 12 plus 2 times 35.5, and that's 83. But we know that our molecular mass is 166. Well, how did we get from 83 to 166? You would just divide the 166 by 83 and you get 2. So that means that we have to take everything in the CCl2 and we multiply it by 2. So that's why it's C2Cl4. All right, up here. So then 13, 14, 15 are all pretty simple. They're just straightforward from the book. Page 172, when a chemist adds extra reactant to verify the other reactant is the limiting reactant, what is he doing? He's adding excess reactant. 14 on page 174, please know the definition of Gay-Lussac's law. And then 15, also straight from the book, it's just that bold-faced word on page 187. Molar mass is the mass of 1 mole of a given compound. So that's about all. Thank you so much. Let me know if you have any questions.